My presentation is on bio-based aircraft for green aviation. My name is Kiran, and I was working with Rolando Perez and Jessica Snyder, who I believe are both in this room, as well as at NASA Ames Research Center in the lab of Lynn Rothschild. So why bio-based aviation? So right now, two of the biggest emerging commercial uses for drones are firefighting and agriculture. So in firefighting, often they'll be used to start controlled burns that will allow firefighters to essentially backburn an area that a wildfire is creeping towards, which allows you to create a dead zone where the fire can't burn. And they're being looked at for that application because you don't have to risk helicopter and pilot to fly about 100 feet above the fire and drop little balls full of gasoline on it. And they're also being looked at for use in agriculture because they're a low-cost way that farmers can upscale and monitor crops without having to be out there every day. There's a lot of research into using them to make agriculture more symbiotic with the world around it. However, drones are made of plastic for the most part, and plastics have extreme problems in both of these use cases. So when plastics combust, they produce a wide variety of different chemicals, many of which are toxic to us, to the environment, to animals. And when they break down and are exposed to the food supply, they can actually be ingested in the form of microplastics, something that you've probably heard about, and can have a knock-on effect on a wide variety of different bodily systems. So obviously, both of these are reasons why we may want to try to replace plastics in drones. So I was working with something called mycomaterials, a name that it's a portmanteau of materials and myco, which is the prefix that refers to things made of fungi. So many of you have probably seen something like this at some point in your life. A log in the woods covered with turkey tails is what I learned to call them. There are different names all over the world. But what you don't see when you look at this is actually a dense network of hyphae, which are the cell structures of these fungi that penetrate through the material that they're growing on. And this network is called mycelium, and it allows the fungi to have nutrient exchange and to have a physical linkage to this material. So the cell walls along these hyphae, which look like this at a microscopic scale, are made with a high percentage of chitin and chitosan. Chitin you may be familiar with. It is the thing that the shells of horseshoe crabs are made of. It's extremely strong. It has an extremely high strength to weight ratio. Combining that with the fact that these hyphae grow in these dense three-dimensional branching patterns, the introduction of these mycelium to a substrate opens the possibility that you could actually use these to bind a loose substrate together. So some of the advantages of mycomaterials, they are a much lower carbon alternative to plastics. While they're not zero carbon, they are eukaryotes like us, so they produce carbon dioxide through cellular respiration, but they don't produce that much more than us. And compare that to plastics, which involve mining petroleum, refining it, transporting it, heating it. All of those require large amounts of energy and produce high carbon emissions. Another advantage is that they're easily customizable. As an experiment to see how fine of detail I could create, I made this mold of the NASA logo. And that, for scale, that arc that stretches around the A and the S is about 1 millimeter wide. So as you can see, you can create very detailed shapes using this, similar to what you can create with, say, injection molding in plastics. They're also biodegradable. There's a lot of research now showing that microplastics are getting into our food supply and our air and our water and our bodies, and this is not good. In addition, the plastics that we produce now will still be here 1 million years from now. And so using materials that would biodegrade would be an extreme benefit. And not only do they biodegrade, they will actually help other materials degrade because these fungi, saprotrophs, are also known as white rot fungi. They're actually part of the natural process of decomposition. So if materials like this were still bioactive and were introduced to, say, compost, it would actually help the process of breaking it down into soil. Another potential advantage is that they have an extremely simple supply chain. So going back to the plastics example, you have petroleum that's often mined in the Middle East or Russia, that's then transported across the world to a different location where it's purified and formed into the proto-materials for plastics, which then are transported elsewhere. It's an extremely complicated supply chain that poses a risk for our economic systems and for geopolitical security. In contrast, these are formed from materials that anyone has access to, wood chips and fungi that are endemic to pretty much everywhere on the planet. And so, as you can imagine, it's a lot easier for anywhere to produce these. And finally, one of the most interesting things is the potential for additional biological functionality. So because these are living organisms, or they can be, you can add other functions to them. For example, a coworker of mine is working on trying to modify them to actually bind to metals. But my personal favorite is the fact that they're self-healing. So when I first made this mold, it cracked when I pulled it out of the mold. You can see that right there in the zoomed in image. And when I played with it like this, gave it some motion, it would actually wiggle back and forth. So I dripped water on it and waited 2 days. And it turned into a solid block. Now, as you can see, it's gotten a little fuzzier. Some of the detail has been lost, but that piece that extends from the side is completely solid. And that is incredible, in my opinion. So what comes next? Scientists have been optimizing plastics since the late 1800s, but fungal biomaterials were first theorized in the early 1990s. So plastics have a century of a head start, and we need to understand more about these. So research suggests that we can use these for a broad variety of applications, from fabrics to foams to hard materials to concrete-like materials, but we just need to test it. So we need a further understanding of two main categories: the limits of the material and the biological endurance. So the limits of the material is the classic material science questions. How strong is it? How much can you pull it? How much can you push it? How much can you twist it? Etc. And this is just needed so we can start applying these two situations in the real world. But another interesting thing that you don't get with a lot of material science is biological endurance. So I've hinted a couple times that these materials can either be alive or not. If you dry them out, they will inactivate. But as you saw, if water is added, they can actually reactivate. We need to understand the upper limit of what will actually allow you to sterilize these materials so they stop being biologically active. And the counterpoint to that of how much can these take and still be biologically active? So to sort of answer both of those questions, I decided to look at the responses of these materials to fire. So there's actually been a decent amount of prior research on this after the 2017 Grenfell Tower fire, which was a fire in an office building that spread extremely rapidly through plastic-based foam materials used as cladding. And after that, there was a big push to use biological materials for building, because one of the things that you see if you look at this image is the smoke is black. It's thick and black. Smoke on its own doesn't have a color. It's a light gray. It's not that dark. That dark is coming from toxic chemicals being produced by these burning foams. And often in cases where you have a fire in a commercial area, often what kills more people is smoke inhalation of these toxic compounds. However, unlike plastics, biomaterials produce mostly carbon dioxide and water as combustion products. If you've ever had a campfire, that's biological materials burning. And so this could present a way that we could make burning safer. In addition, when chitin, which I mentioned earlier, combusts, it can produce a lot of flame-inhibiting compounds. And there are also some research to suggest that additives can actually decrease the flammability even further. So that's what I decided to focus in on. So I wanted to understand the response of these materials to flame, understand the limits of their heat tolerance in non-igniting conditions. So how much can you bake them, essentially? And then try to engineer these materials to be more fire resistant. So the first step in this was characterization. Because I was working at NASA, one of the things we were interested in is space applications. And for space applications, there are very specific standards about flammability. Specifically that in this test, which is called Test 1 creatively, and conforms to NASA standard 6001, you ignite a specimen that's about this long at the base, and you see how much of it burns before it stops burning. And the burn length has to be less than 15 centimeters for your material to be considered flight qualified. And in addition, there's a paper placed below it that has to not catch on fire from anything falling. However, this test is very high fidelity, but it's very expensive. And so we wanted to look at trying to do some basic characterization on our own. And so this was my solution, in-house flammability testing. So in this video on the left, you can see me holding a piece of these biomaterials over an open flame. And as you can see, it starts burning, but after a minute, you'll notice that the flame actually disappears. It is still smoldering. And so this is a time lapse taken of that same brick after the flame extinguished, placed in a ceramic dish. So you can see that over the course of several minutes, the flame is still slowly consuming the material. And then the image in the middle that you see was the catch paper that I placed below it, very high tech. Piece of lined paper weighed down with a couple of metal rods, but it worked. And as you can see, it didn't ignite. The only things that fell were a couple of small pieces of ash. So then I wanted to look at actually making them more flame resistant. So there's research right now that suggests that adding a silicon source and growing these materials in a silicon source can increase the temperature at which they ignite, decrease the height that a flame gets to, and make the burning of them less hot. So I hope to build on the existing research by testing other sources of silicon. The research out there was using one specific form of silicon that is not ideal for working in biological materials. However, I ended up having issues obtaining different silicon sources. So I realigned this to examine the potential for in situ resource utilization, or ISRU, which refers to obtaining needed materials from the place you are on the moon or Mars. And one of the things that's present on both the moon and Mars is silica, silicon dioxide or sand. And so I looked at actually breaking down bioavailable silica from sand using the same chemical that fungi naturally do in higher concentrations, oxalic acid. So in this image on the right, taken under a 400x magnification light microscopy, you can see a grain of sand. That's the large chunk on the right. I sifted the sand grains to between 0.075 and 0.18 millimeters. And that is where, and then the small stuff everywhere else is actually the silica being broken off of that sand piece. So these were some more pictures. On the left, this is me combining that liquid silica source with the materials. And then on the right, this is one of the finished material coupons, which I am planning to do ignition testing on and quantify their flammability. I'd like to thank Blue Marble Space and the YSP for making this possible, as well as Lynn Rothschild and her lab at NASA Ames. I'd also like to thank all of my collaborators, the people I've worked with both through the YSP and at Ames Research Center. And I'd like to thank all of my mentors. I would not be here without them. And finally, I would like to thank Swarthmore College, my college, for giving me funding to support this research. Does anyone have any questions?
Awesome. It was very cool. We can allow for a question here. I think we have time if there are any in the audience. Sanjoy has his hand popped up. Sanjoy?
Kiran, thanks very much for this fascinating presentation. Are there home kits that exist that we can buy or to play with this stuff?
Yeah, so there's a company called Ecovative that makes this as a commercial product. You essentially receive a starter material that is already seeded with mycelium. You have to add water and leave it in the sun for a bit to heat it up. And then you can mold it into whatever shape you want, let it sit, and it will form itself into a solid material.
Sorry, I didn't catch the name of the manufacturer.
EcoVeda.
Can you put that in the chat?
Yes.
Amazing talk. Thank you.
Thank you.